Hello everyone, I am Louis Dever from the Université in Toulouse, and today we're going to spend some time to talk about mechanical decision making in ants. But first, what is a mechanical decision? Well, we'll define it as a decision to move an object from A to B, meaning applying a certain force, F, on a certain distance, D. In physics, we call that a mechanical work. It will be our measure of cost, and is usually measured in joules. Following that definition, ants make these kind of decisions all day long, carrying food items, building the nest, or clearing their way, like on the examples here. But are they good at it, mechanically speaking? Do they take the good decision among several options? And if so, how? To address these broad questions, we wanted to make things a bit simpler, studying this decision-making process in one dimension only. To do so, we studied the shift in decision in the context of gallery clearing. It can happen when a gallery is hindered by a small object and ants need to extract the obstacle on either ends of the gallery. To study that phenomenon, we made a simple setup. So we used pipette as standardized gallery and boxes on each ends. The nest box, always downhill, and the foraging box, uphill. A stick is inserted and ants will pull and drop it sequentially and eventually evacuate it by either options. So we control the initial position of the stick as well as the slope angle on the gallery and noted the extraction direction, whether uphill or downhill. On another set of experiments, we observed about 3,300 ants' mandibular grasp and both directions as well. Through a simple physics experiment, we estimated the coefficient of friction of the stick with the tube, thus allowing us to compute the theoretical force needed to move the object. This estimation allows us to compute the point where the ant will need the same amount of work to extract the obstacle in either direction. We've grouped the data as follows. On the x-axis we have the slope angle, on the y-axis we have the distance to the nest, and the color states the probability of extracting the stick to the foraging area up the slope. The yellow line is the set of position that needs equal amount of work to extract the object either direction, and the purple line is the line where ants choose with equal chances. We note there is quite an offset between those two lines. Ants tend to extract downward even when it requires more mechanical work. However, when doing the same kind of plot for the mandibular grasp, we note that there is an overlap, meaning ants make random grasping decisions when both options are equivalent. But how optimal is that then? Well, we can plot the decisional shift according to relative fitness to see that more clearly. On the x-axis, the relative fitness of the upward solution, and on the y-axis, the probability of choosing said solution. When on the x-axis we are at 0.5, both options are equivalent. So there is a clear bias in the collective behavior on the left, but the shift in decision is well tuned on the individual one. With further data analysis, we noted that the grasp and pull behaviors were different. Grasp behavior can be solely explained by distance to the closest exit, while pulling behavior orientation can only be explained by mechanical cues like force or work. So, alright, we know the direction ants will take for a stick position and that it is rather correct usually. But we don't know when or where is it going to drop it. Turns out, if the task is difficult, the ants pull on shorter distances. However, besides of doing survival analysis on the distances, we did some on the mechanical work as well. So it means that we studied the risk of dropping the stick after the next joule is exerted. We know that for all angles and all directions, for a broad variety of task difficulties, the amount of work exerted is roughly the same. We then model the extraction process in ants in two steps. The ant grasps the stick and chooses a direction with the data from earlier, and then she moves it. When implemented this constant work rule into the moving component, we were able to reproduce the decisional bias at the collective level. More importantly, we were not able to reproduce such bias when implementing other non-mechanical cues. So, to wrap it up, the collective extraction decisions are mechanically suboptimal, yet the individual pulling decisions are mechanically sound. We noted that the mechanical grasp are based on the distance. Ants will choose the closest exit, but they probably have a gauging role, because the transformation from a grasp to a pull is based on mechanical cues. We can only explain that statistically with mechanical cues. And the investment in the task fits rather well, hypothesis with mechanical cues as well. Thanks for your attention.